All right, so number one on the test review is just going to be to find the following. So first off, let's find secant of pi over 3. So secant, that's just going to be 1 over cosine of pi over 3. And cosine of pi over 3, that will be 1/2. So we'll have 1 divided by 1/2, which will equal 2. So first problem, not too bad. Second one, cosecant. So when we're doing cosecant, we got to remember that's 1 over sine. So cosecant of 11 pi over 6 is 1 divided by sine of 11 pi over 6. Well, sine of 11 pi over 6 is negative 1/2. So we end up with a negative 2 here. Tangent of pi over 3, you might have this one memorized. It could be square root of 3, and that's just it. But just in case, that is, excuse me, not tangent. Tangent is always sine of your angle, pi over 3, divided by cosine of your angle. Well, sine of pi over 3, that is square root of 3 over 2. While cosine is going to be 1/2, leaving me with the answer, as we stated earlier, of square root of 3. Last but not least, cotangent of negative pi over 4. Well, cotangent is cosine divided by sine. Now, alternatively, you could use 1 over tangent if you have tangent of negative pi over 4 memorized, and actually in this case that's easier. So 1 over tangent also works, but cosine of negative pi over 4 is positive square root of 2 over 2, while sine of negative pi over 4 is negative square root of 2 over 2, which cancels out to give you negative 1 as an answer. The whole intent behind this problem is that you guys know exactly what these guys are and how they translate to this next line over. Secant, 1 over cosine. Cosecant, 1 over sine. Tangent, sine over cosine. Cotangent, either 1 over tangent or cosine divided by sine. See you at the next problem. All right, so for this problem, this is number 2. We're given that sine of theta is 7 over 8. And that theta is in quadrant 2. Now you're asked to find all the other trig functions. So that's what we're going to be doing in this problem. Let me straighten that up real quick. There we go. Well, whenever I give you one of these problems where you need to find all secant, cosecant, cotangent, and tangent, what you need to always have is sine or cosine. Now I can do that in multiple ways. I could give you a unit circle with x and y coordinates, cosine and sine. I could just straight up give you sine and cosine. Or last but not least, and most tricky, I could give you a problem like this. The reason that this gives you sine and cosine is because of a 5.2 problem. So remember that we always have sine squared of theta plus cosine squared of theta equals 1. That's going to be the thing that we utilize. We have what sine of theta is. So this statement translates to 7/8 squared plus cosine squared theta equals 1. Now when I square this fraction, I'm going to square both top and bottom, and then I'll subtract it over, giving me cosine squared of theta equals 1 minus 7 squared is 49, 8 squared is 64. So 1 minus 49 over 64. Which that'll simplify out to be, I guess, 15 on top. 15 over 64. So from here, we can square root cosine. When I do that, I get cosine of theta equals plus or minus the square root of 15 over 64. Now remember, when we square root a fraction, that's the same thing as square rooting both the top and bottom. So really what we get is plus or minus the square root of 15, which doesn't really simplify down, divided by the square root of 64, but we know what that is. That's 8. So now that we have cosine of theta equals plus or minus something, it's up to us to determine, well, are you the plus or are you the minus? So that's where this quadrant information comes in. In quadrant 2, the upper left-hand corner of the unit circle, cosine, the x-coordinate, will be negative. So I'm going to choose cosine of theta equals negative square root of 15 over 8. Now we have enough to solve the problem. All right, so we were asked to find every single trig function besides the ones that you were given. So now we got sine and cosine, we can develop the rest of them. Let's start with tangent. Tangent of theta, remember that is sine divided by cosine of that angle. So I'll have 7/8 divided by negative square root of 15 divided by 8. Now multiply by the reciprocal, giving you negative 7 over the square root of 15. Now on the test, I'm going to ask you to rationalize this problem. So what you need to do is multiply on top and bottom by square root of 15 to give you that tangent. Ultimately is negative 7 times the square root of 15 divided by 15. So, okay, I just want to make sure that was legible. So remember, we just multiplied by square root of 15 over square root of 15. Square root of 15 is multiplied to give you 15, and we just get negative 7 times square root of 15 divided by 15 as your answer. Secant is 1 over cosine. So 1 divided by negative square root of 15 over 8. Well, we multiply by the reciprocal, giving me negative 8 over square root of 15. Yet again, let's rationalize the denominator by multiplying on top and bottom by square root of 15, giving me negative 8 square root of 15 divided by regular 15. Penultimately, because we also need to find cotangent, let's get cosecant. Cosecant is 1 divided by sine. 1 over 7/8. Now multiplying by the reciprocal, flips that around, gives me 8/7. No need to rationalize this one. Last but not least, if we do cotangent of theta, I know I'm running out of room here. That is cosine divided by sine. So negative square root of 15 over 8 divided by 7 over 8. Which ultimately gives me the answer of negative square root of 15 divided by 7. Now I'll get that from multiplying up by the reciprocal. So the thing you can check here, if you want to check your work kind of quickly, would be, okay, in quadrant 2, if you remember the mnemonic A Smart Trig class, where the unit circle kind of has something like that going on. A stands for everything will be positive, all positive. S, quadrant 2, stands for only sine will be positive. Everything else should be negative. Well, sine and its flip being cosecant. If we check that out, sine is positive, cosine is negative, tangent's negative, secant's negative, cotangent's negative, and last but not least, cosecant is positive. So we are right that in quadrant 2, only sine and cosecant should be positive. So remember, all functions positive here, only sine functions positive here, only tangent functions positive here, only cosine functions positive here. It gives you a nice way to check it. Something like this will absolutely be on the exam, so get ready for it. All right, so for number 3, we're given 2 right triangles, and we need to go ahead and film the, or not film, sorry, looking at the video. We need to go ahead and solve these out for all missing angles and missing sides. So the things that would come to mind are right triangle trigonometry, SOHCAHTOA, And then also just any kind of triangle stuff that I know, like the Pythagorean Theorem, and that angles add up to 180 degrees. So starting with this guy, the top one on your review, we notice that we're missing only one angle. So since we have 180 degrees in a triangle, that better equal 90 degrees, my right angle right here, plus 30 degrees, plus whatever B is, which will ultimately give you that B will equal 60 degrees. Now, I don't need you to show me that work. I can assume that you guys can do that one in your head, but that's how you show it if you're curious. So B is 60 degrees, capital B that is. Now I need to get my hands on C and B. What I'm going to want to use is this 30-degree angle right here. So notice that C is the hypotenuse. I need to find the hypotenuse and the adjacent side to it. Well, since I'm given the opposite side, I want to invoke trig functions that do the opposite side when we think about SOHCAHTOA. In particular, if I look at sine of 30 degrees, that will be my opposite side, 7, divided by my hypotenuse, C. Well, this tells me right here that if I kind of multiply up by C divide over, that C better equal 7 divided by whatever sine of 30 degrees is, which since that's such a nice angle, it turns out it's 1/2. So 7 over 1/2. So ultimately, C equals 14. So this is what we're going to do to go ahead and get our sides and angles. Now, if I want to get my hands on B, what I need to use is, well, we can either use cosine, now knowing that C equals 14. We could also use our 60-degree angle B, but the one that I see right away is just going to be tangent. So tangent of 30 degrees, and like I said, multiple ways to skin a cat on this problem. Tangent of 30 degrees will be my opposite side, 7, divided by my adjacent side, B. Playing the same game with it, we notice that if I multiply out by B, divide over by tangent of 30 degrees, I get that B equals 7 over tangent of 30 degrees. Tangent of 30 degrees turns out to be square root of 3 over 3. I can multiply up by the reciprocal, similar to the last problem, and I'll get 21 over square root of 3. If I multiply by square root of 3 on top and bottom, I'll get 21 square root of 3 over 3, which ultimately simplifies down to B equals, cancel out a 3 from the 21 and the 3, 7 times the square root of 3. So a lot of steps in finding that last one. Maybe tangent wasn't the nicest way to do it, but so long as you get B equals 7 square root of 3, C equals 14, and capital B equals 60 degrees, you're good to go. I'm going to erase my work now, so feel free to pause it. And let's tackle the other guy now. All right, so I'm over here. First thing I'm going to get is my hands on the angle. So notice I got a 90-degree angle, a 60-degree angle, and I need angle A. Well, we play that takeaway from 180 game. 180 minus 90 is 90. 90 minus 60 is 30. That has to be A. A is 30 degrees. Now what I'm going to utilize, similar to the last problem, is the 60-degree angle. So what do I have compared to 60 degrees? Well, I have the opposite side, and I need to find the hypotenuse. Sine relates opposite and hypotenuse. So sine of 60, the opposite side being 10, is the opposite divided by the hypotenuse, C. Now this looks a little bit weird with the hypotenuse being on bottom, but remember the hypotenuse is the side opposite of the 90-degree angle. Do some solving around, multiply up by C, divide over by sine of 60, and we'll get that C equals 10 divided by sine of 60 degrees. Like I said, you can use your 30-degree angle that you just found. That might be a little bit more useful. You can use a lot of things here. This is just what I'm doing. Well, sine of 60 degrees, that's a nice one. That's square root of 3 divided by 2. I multiply by the reciprocal, giving me 20 over square root of 3, because this guy will multiply on top, the 2 and the 10 combined. And I rationalize, giving me 20 square root of 3 over 3 as my hypotenuse. Last but not least, to get my hands on A, what I'm going to invoke is tangent. Tangent of 60 degrees, that is my opposite side, 10, divided by my adjacent side, A. Similar manner to how we've been solving it, A better equal 10 divided by tangent of 60 degrees. Now, tangent of 60 degrees is just square root of 3, so we get 10 divided by square root of 3, which when we rationalize by multiplying on top and bottom by square root of 3, gives me 10 square root of 3 over 3. That's what A will be. 20 square root of 3 over 3 is what C will be. And last but not least, A, capital A, is 30 degrees. And that's it for problem number 3. All right, number 4 says find X right here. Well, we're given a right triangle. I know the picture's a little confusing. 119 is meant to be the far left side on this leg of the triangle right here. So we need to utilize this information, 70 degrees, 26 degrees, and the opposite side of both of those angles, that so happens, in order to find X. Well, we got to gather what we can find in this problem. What we can notice, yeah, it's popping up, okay, is I would be able to find this side, maybe I'll call it Y, by doing something with 70 degrees, and I'm also going to be able to find this whole side, Z. Yeah, maybe it's not popping up the best. There, we'll give it a cool little white and purple going on. It's like the Vikings, I guess. So I can't find both Z and Y here. Now, the thing to notice will be that if I take Y away from Z, that'll leave me with just X. Now, if you didn't see that right away, the thing to notice is that X plus Y equals Z, and then when you take away Y, giving you Z minus Y on the right-hand side, you recover X. So either way, we're going to be able to come up with X based on the whole side Z and a part side Y. Now, why do I have to get these involved? Well, it's because they deal with right triangles. X doesn't really deal with a right triangle on its own. Notice it's kind of more part of this obtuse triangle. So if I can incorporate Y, which belongs to this right triangle, and Z, which belongs to this whole right triangle without that middle leg, then I'm good to go. Now, in particular, let's find Y. How do I get Y in the picture? Well, that's the adjacent side of 70 degrees. Well, I also have the opposite side. The thing that relates opposite and adjacent is tangent. So tangent of 70 degrees better equal the opposite side of 70 degrees, 119, divided by the adjacent side, which is Y. Multiply up by Y, divide over by tangent of 70 degrees, you get that Y is equal to 119 over tangent of 70 degrees. Now for Z, we do a similar thing. Notice that 119 is the opposite side of 26 degrees, and we're after the adjacent side of 26 degrees, which is Z. Yet again, opposite and adjacent are related through tangent of that angle. So tangent of 26 degrees better equal, or the opposite side, 119, divided by the adjacent side, Z. Multiplying up, dividing over, this tells me that Z better equal 119 over tangent of 26 degrees. Now I'm going to assume you don't have a calculator as far as this exam goes, so what you could write as an answer therefore, based on this, is that x equals z, 119 over tangent of 26 degrees, minus y, which is 119 divided by tangent of 70 degrees. If I give you nice angles, or if I give you units, I expect you to work out the nice angles, like if it was tangent of 60, tangent of 30, you should know those ones. And if I give you units, like, hey, this is in inches, you better include those as well. All right, now for this problem, number 5, part A, we were asked to find both the amplitude, equation of the midline, phase shift, and period of this function, as well as graphing it. So it's kind of a big problem, but let's dive in. So very first, I'm going to start with the amplitude. So remember when I have something of the form A cosine or sine of bx minus c plus d, that the amplitude is going to be the absolute value of A. It's just going to be the number out here, which is 2. The period is going to be 2 pi divided by the absolute value of B. In this case, B is 2, so we just get a period of pi. The midline is going to be the equation y equals d, where d is the number out here, and you need y equals, so heads up, therefore, the equation of the midline is y equals 1. Last but not least, the phase shift, meaning how far over to the right or left I moved, was given by c divided by b. Now in this case, c, notice the negative right here. The negative is meant to be there, so c is positive pi over 2. So pi over 2 divided by b, which was 2, gives me a phase shift of pi over 4. So therefore, I move to the right pi over 4 from a regular sine or cosine function, in this case, cosine function. All right, so that's how we collect all of those. Definitely will be a problem on the exam, hopefully a nice gimme. Now you got to graph it. So I'm going to go through the 5-point method. Now remember, so I'm going to gather my 5 points over here. So the first point, x1, comes from when the inside equals 0. So if you don't remember the formula, remember that you can solve for the first point by setting the inside of cosine, 2 theta minus pi over 2, equal to 0. Now it turns out this will actually line up with the phase shift, so there are plenty of shortcuts that you can really do for these problems. So if I solve for theta, by adding over the pi over 2 and dividing by 2, I get that my first important point is pi over 4. Now my second important point comes from when the inside of cosine equals pi over 2. Yet again, by adding over pi over 2 and dividing by 2, I'll get my second important point is pi over 2. Because pi over 2 plus pi over 2 is pi, divided by 2 gives me pi over 2. Now notice that the common gap to get from pi over 4 to pi over 2 is pi over 4. So it's kind of an important thing to have down right there. So therefore, when I go ahead and get my next point, all I need to do is add pi over 4 to pi over 2, the common gap, and that will give me an important point of 3 pi over 4. Next important point, add pi over 4 again, I'll get regular pi. And last but not least, my last important point, theta 5, will be pi plus pi over 4, giving me 5 pi over 4. Now, if I may erase, remember pause if you need to. What I now need to do is get the y coordinate. So, when my, just trying to think about how to write this. What I'm just going to go ahead and do is find f of pi over 4. F of pi over 2. I think this is the cleanest way to write it. F of 3 pi over 4. F of pi. And f of 5 pi over 4. Yet again, there are plenty of shortcuts, so keep that in mind. Since I have the important points kind of labeled right here, I'm going to go ahead and erase that work. Now, I wouldn't do this if it weren't on an exam. You know, it's a big problem. I recognize that. But when I plug all these guys in, well, when I plug in pi over 4 to cosine of here, I'll just get cosine of 0. Well, cosine of 0 is positive 1, so I'll get 2 plus 1, 3. When I plug in pi over 2, by design, the inside will be pi over 2. You can always check that out. Cosine of pi over 2 is 0, so I get positive 1. F of 3 pi over 4, well, by design, that important point makes the inside of cosine just regular pi. Cosine of pi is negative 1. Negative 1 times 2 is negative 2, plus 1 gives me negative 1. When I plug in pi, by design, that made the inside of cosine 3 pi over 2. Cosine of 3 pi over 2 is 0, so I just get positive 1. And 5 pi over 4, by design, makes the inside of cosine 2 pi. That's the whole reason we do these important points. They make the inside of cosine these nice quadrantal angles. But cosine of 2 pi, that is just 1. 2 times 1 plus 1 gets me back to 3. Ultimately, to graph this guy out, all I'm going to do is clearly label everything. So 1, 2, 3, and then down to negative 1. Draw my x coordinates. Pi over 4, pi over 2, 3 pi over 4, pi, and 5 pi over 4. And then just label my points. Positive 3 at pi over 4, then to positive 1, to negative 1, to positive 1, up to 3. And then just make it look like a cosine function. So something like that. If I asked you to do more periods, all you would do is just kind of repeat, just copy paste this image right next to it, and you're good to go. All right, for 5 part B, they're given a function g of theta equals 3 times tangent of pi over 2 theta. So with this guy right here, what we're going to want to do is first off find stretching factor, period, and equation of the vertical asymptotes. This one just takes the memorization for the last one, and well, really for all of them. So first off, stretching factor. That is the amplitude of your tangent function. So that is just the absolute value of a, which is the number out front. Your stretching factor is just 3. Your period will be pi, the typical period of a tangent, just like 2 pi in sine and cosine, divided by the absolute value of b. So with sine and cosine, it's 2 pi divided by absolute value of b, the regular period divided by b. And with tangent, it's pi, the regular period of tangent, divided by b. b in this case is pi over 2, so I'll get pi divided by pi over 2. When I multiply by the reciprocal, I'll get a period of 2. Last but not least, the equation of the vertical asymptotes. This one's a little bit goofy. It's your phase shift, C over B, plus pi over 2 times the absolute value of B times K, where K is an odd integer. If you just put K odd, I know what you mean. Just want to make sure I wasn't leading you wrong. Yeah, so like I said, these ones just come down to memorization, right? Even myself, like sometimes I don't remember it, so just make sure you have it down. All right, in this case, we do not have a C term. So what we get is 0, right? The C would be the thing that's subtracted away from the theta term. So we have 0 divided by pi over 2, which is just 0, plus pi over 2 times B. So pi over 2 times, well, the absolute value of B, but that's just pi over 2, times K, where K is odd. And when we simplify this out, and notice I'm always putting x equals because it is a vertical line. X equals, well, the 2's cancel here, and then the pi's cancel, so I'll just get 1 times K. So x equals K, where K is odd. And like I said, I shouldn't have boxed prematurely. I need x equals here. That's important. So x equals K, where K is odd. To be honest, this is probably the part I'm going to ask you about tangent. I'm going to more care about you graphing sine and cosine. Hint, hint. Thanks for watching the video. Now I'm going to pause it here, so feel free to take it, like pause it. So I'm going to erase. Now, just like last time, we need to get our important points for tangent. So your first important point comes from when the inside, pi over 2 theta, equals negative pi over 2. This happens when theta, if I divide by pi over 2, equals negative 1. Now our second important point comes from when the inside equals negative pi over 4. If I divide over by pi over 2, I'll get theta 2, my next important point, is negative 1/2. Now this tells me the gap. The gap better equal 1/2. So my next important point, I just add 1/2, is 0. My next important point beyond that, theta 4, is positive 1/2. And I add 1/2 one more time to get my last important point of positive 1. Now remember, with tangent, your first and last important points are vertical asymptotes. It's where the tangent on the inside is negative pi over 2 and positive pi over 2. So that's going to be the important part. This will be a vertical asymptote, as well as this guy. Now with the middle three, I can actually figure out what the y-coordinates are. F of negative 1/2. Well, by plugging that in, I'll get 3 times tangent of negative pi over 4. But tangent of negative pi over 4 is just negative 1, so this gives me negative 3. Plugging in 0 gives me 3 times tangent of 0. And that's just 0. Tangent of 0 is 0. 3 times 0 remains 0. Last but not least, plugging in 1/2, positive 1/2, gives me 3 times tangent of pi over 4. But tangent of pi over 4 is just 1. So I end up getting 3 here. So if you do not mind me erasing one more time, all I do now, since you guys can see over here, I'll go ahead and draw it over here, is I just draw and clearly label my points. So let's say 3 right here, negative 3 right here, 1/2, 1, negative 1/2, negative 1. I draw my vertical asymptotes at the first and last important point. And then I clearly label. At negative 1/2, I had a y-coordinate of negative 3. At 0, I was 0. And at 1/2, I was 3. So long as I can label or just read your points, you're good to go. And then play connect the dots tangent style. It doesn't have to be perfect, as mine clearly demonstrates. Definitely not perfect here, but that's what you should look like for this problem. So yet again, find your 5 important points. Well, just find your first 2 when the inside equals negative pi over 2 and negative pi over 4 respectively. Get your hands on the y values for the middle ones and recognize the last one and the first one are vertical asymptotes. Then graph it by playing connect the dots tangent style. All right, for number 6, this is going to go ahead and find the equation. So I know it's probably a little hard to see what this looks like. I didn't have any more colors, so I apologize. But what they want are the period, equation of the midline, amplitude, and phase shift. Now, importantly, we are saying, if I don't mind me looking, that this is a sine function. And then last but not least, they want you to tell me what the equation is of this sine function. So I know it's something of the form a times sine of bx minus c plus d. So very first and foremost, let's talk about the amplitude. The amplitude, that's the measure from your midline to a peak or a valley. It looks like that's just going to be positive 2. Now, importantly, this came from the absolute value of a, and if you don't have good reason to change it from being positive, do not claim then that a is positive 2. The only time you would change this is if you have some kind of vertical reflection going on, right? Because a is multiplied outside. Remember, vertical reflection outside multiplication by negative. All right, so we'll use that later. Or let's go with the equation of the midline. Remember, that's just kind of the line that goes right through the middle. In this case, that's at y equals negative 3. But remember, the equation of the midline came from y equals d. So d better equal negative 3. We'll use that later. Now we need to know our period. The period is the distance from either valley to valley, peak to peak, or other corresponding point to other corresponding point. In this case, we have kind of 2 nice valleys to choose from or 2 nice peaks to choose from. I'm going to measure from peak or from valley to valley. Well, that's from negative 1 up to positive 3. I covered a distance of 4. So my period is 4. Now notice that's also the distance from peak to peak, from negative 3 up to positive 1. 1 minus negative 3 is positive 4. Now remember, this came from the equation 2 pi divided by the absolute value of b. Now, if you don't have a good reason to make b negative, keep it positive. And always keep b positive. This is going to be just kind of one of those things that just works. If I multiply up by b and divide over by 4, I'll get that b equals 2 pi over 4, which is pi over 2. Yet again, we'll hang on to this and use it to go ahead and fill out our equation. Last but not least, we need to get the phase shift. Now remember, your phase shift is the amount over that you are positioned, the horizontal displacement, from a regular sine function in this case. If I said it was a cosine function, it's your displacement from a regular cosine function. Now what that means is how far, with the sine function, is how far over do you have to move this to get a midpoint on the line x equals 0, on the y-axis. If this were a cosine function, I would need to measure how far over a peak is. So this distance right here. But since I'm talking about a sine function, it turns out the phase shift is 0 because we already have a midpoint at the line x equals 0, or at the y-axis. Like I said, if this were a cosine function, our phase shift would be 1 or -3. Take your pick, it doesn't matter. Well, remember, phase shifts came from the equation c over b. Well, we already got our hands on b, so we need to just find c. Well, turns out c is just going to be 0 since it's equal to 0. So this tells me right away, c equals 0. So we got our phase shift, amplitude, midline, and period. Now we just need the equation, which is why we got all those things. Ultimately, your equation is y equals 2 sine of pi over 2x minus 0, so I do not include minus 0, minus 3, because that's what d was. This is more the point I care about. I'll probably just say, hey, figure out the equation of it. You know, I'll leave this stuff for the other one, but you kind of have to go through and use this anyway to get the equation. So use your period, amplitude, midline, and phase shift to recover A, B, C, and D, which allow you to go ahead and state that. By the way, great spot to use a graphing calculator to help if you have one available. All right, so for number 7, I'm asking you to find a bunch of things related to inverse, cosine, sine, and I guess that's it for this one, right? Be ready for also inverse secant, cosecant, cotangent, and inverse tangent. But really, these are the guys I care about. Everything comes from sine and cosine, so you can kind of recover a lot from that. But let's talk through how you would do this stuff. Part A, what is inverse sine of negative square root of 2 over 2? Yes, you could just plug this into a calculator. What I want to see is your work, okay? So it's kind of like when I said, hey, evaluate log base 10 of 1,000, right? I want you to show me the translator step, and that's what I want you to do here. If I call that equal to some degree theta, or some angle theta, this thing translates to sine of theta equals negative square root of 2 over 2. Now you have to ask yourself, where does theta, or where is sine of theta equal to negative square root of 2 over 2? Well, if we think about it on the unit circle, that's either in quadrant 3 or quadrant 4 because sine is the y coordinate. So it turns out the angle that works is going to be negative pi over 4, which if I draw a unit circle, you know, the two spots it would have worked were either here or here. But importantly, the domain, or excuse me, the range of inverse sine is the right half of the unit circle. So we have to make this angle right here, which was negative pi over 4. So your answer is negative pi over 4. Inverse cosine of negative 1/2, we treat the same way. Okay, let's set that equal to an angle. This statement translates to cosine of theta equals negative 1/2. Now we got to ask ourselves, for what angle is the x-coordinate negative 1/2? Well, yet again, if I draw a unit circle, x-coordinate negative 1/2 either happens here or here. And yes, I know that's like a unit egg, but I'm not good at art. Remembering the range of inverse cosine being the upper half of the unit circle, we pick this angle, which will be 2 pi over 3. So the range of inverse cosine is from 0 to pi. Last but not least, you can kind of see I have it split into two different portions. This is kind of split because these are all following the same theme, and that one's a little bit different. So last but not least on this side, first off, let's find what cosine of 7 pi over 6 is. So remember when you got kind of two composed functions like this, inverse sine of cosine of 7 pi over 6 always worked from inside out. Cosine of 7 pi over 6 is the x-coordinate at the angle 7 pi over 6. And that will be our negative square root of 3 over 2. So inverse sine of negative square root of 3 over 2. Now, luckily for us, we've just done a bunch of practice problems like that. Let's call that equal to some degree theta. Now, I'm going to disappear for a little bit. I'm sorry. If then I translate that to sine of theta equals negative square root of 3 over 2, I say, hey, when is my y-coordinate negative square root of 3 over 2? Well, that happens either at 5 pi over 3 or 4 pi over 3. But then remembering the range of inverse sine, I choose this guy and say, hey, this guy is just equal to negative pi over 3. So I'll put equals theta, kind of continuing our train of thought. Now, the negative, that's just the negative version of 5 pi over 3. So remembering the range of inverse sine, that's what you end up getting. But it comes from this question here. When is sine of theta equal to negative square root of 3 over 2? This leads me way over here to our last problem. Angle a little bit more, that way it's flat on. Tangent of inverse cosine of 4/5. Now, we're still going to start from inside out, and what we're going to do here is we're going to write inverse cosine of 4/5. I'm going to replace it with an angle. Because that's all it is, right? Let's find the tangent of some angle. Now, what I did there is I said, hey, theta equals inverse cosine of 4/5. Well, hey, we've done that before over here. Let's go ahead and swap it around. Cosine of theta equals 4/5. Well, that'd be kind of nice if I just knew what tangent was from that. But what we can do is use a right triangle. So I love this problem because it involves a lot of things that we know. Okay, cosine of theta, that is adjacent over hypotenuse. So we get a triangle that's looking something like that. We can solve for this side, the unknown side, by using the Pythagorean Theorem. Z squared plus 4 squared equals 5 squared. Now, upon solving that out by subtracting over 4 squared and square rooting, we'll get that z equals 3. Now, ultimately, using this information, we're just trying to find tangent of theta. So all this is side work. Tangent is the opposite side over the adjacent side from SOHCAHTOA. So we end up getting 3/4 as our answer over here. I know I went through these guys kind of fast. Make sure to go look at the 6.3 video if you do need some more help with this. But this problem in particular, I like that one a lot. I'm going to ask you guys probably one of these, this and one of this. So just a heads up. But yeah. All right. First problem in number 8, part A, is evaluate exactly cosine of pi over 12. Now, if this were a problem on the unit circle, you just go ahead and figure out what it is. But pi over 12 is not an angle on unit circle. This is a 7.2 problem in disguise. Well, yeah, it's a 7.2 problem unless you can figure out a way to multiply it by 2, but then you just get pi over 24. Ugh, that's nasty. So 7.2 problem. What you need to do is to figure out a way to write pi over 12 as either two nice angles added together or two nice angles subtracted from each other. So with that in mind, we got to start figuring out what we can maybe go for. When I'm looking at pi over 12, the thing I'm trying to think of are what numbers play nicely with 12. Meaning, what are the factors of 12? Like 1, 2, 3, 4, 6, 12. Right? Those are the ones I'm looking at. And I'm wondering, okay, which ones are within 1 of each other? Because I need a 1 on top. Turns out the nice way to do this is to say pi over 12 can be written as 4 pi over 12 take away 3 pi over 12. Nice, tricky problem here. I need to see this step. Since I'm allowing calculators, if you just tell me what it is, it won't do. Since I can write it as 4 pi over 12 minus 3 pi over 12, I notice that, hey, 4 pi over 12, that's pi over 3. That's a nice angle on a unit circle. 3 pi over 12, that's pi over 4. That's a nice angle on a unit circle. I'm good to go. Now from here, you have to have memorized the fact of how to split up on negative cosine or cosine of an angle minus an angle. This can be split up as cosine of your first angle times cosine of your second angle plus sine of your first angle times sine of your second angle. So just rogue memorization on this portion. Cosine of pi over 3, that's 1/2. Cosine of pi over 4, that's square root of 2 over 2. Plus sine of pi over 3 is square root of 3 over 2. Sine of pi over 4 is also square root of 2 over 2. Now remember, you're just multiplying the tops together. So I get square root of 2 over 4 from this guy. You multiply the tops and the bottoms together, I should have said. I was kind of focusing on the top, my bad. So square root of 2 over 4 plus square root of 3 times square root of 2 is the square root of 6 over 4, giving you an ultimate answer of square root of 2 plus square root of 6, all divided by 4. And yes, you could probably simplify this out a little bit. I can see at least one thing you can do, but I'm totally good with that as an answer. Now pause here. I'm about to erase so we can get into part B. If I can find my eraser. It's been a long day. All right, if we're looking at number 8, part B, this gives you some information about A and our cosine of A and cosine of B. So sine of A is 2/3. Cosine of B is going to be negative 1/4. And now importantly, it says, hey, both A and B are in quadrant 2. Now, what it's wanting you to do from here is to find both sine of A plus B and cosine of A minus B, which will yet again come down to memorization once we get to that step. Well, first thing I'm going to do, since we're focusing on sine of A plus B, is let's recall the formula for that. Sine of A plus B is just sine of A times cosine of B plus cosine of A times sine of B. Well, I have sine of A and cosine of B, so I can just plug them in already. 2/3 cosine of B, negative 1/4. Unfortunately, I do not have cosine of A or sine of B. I need to use right triangles to do that. Now, thing to keep in mind here, both A and B are in quadrant 2. That information is pertinent. If I draw a circle and I look at quadrant 2, I'm going to gather my right triangle because we're going to lean on SOHCAHTOA from this right here. Now, I was asked this in class, why do I draw my angle this way and not like kind of flipped up, if you can imagine that? It turns out that this is your reference angle and it comes from reference angles, which is why they told us about that early on. So, my right triangle looks something like that, where there's my angle, and since A and B are both in quadrant 2, I need to draw 2 copies of these. Or maybe this is my triangle for A, and this is my triangle for B. They're both in quadrant 2, so they both look the same. Right angle, right here. Now I have information about sine of A. It's 2/3. Okay, so the opposite side is 2, and the hypotenuse is 3. I have information about cosine of B. That's -1/4. Well, since we're in quadrant 2, notice that the x-coordinate is going to be negative. So my adjacent side, representing the x-coordinate down here, which is why I like to draw the unit circle, will be negative, while my hypotenuse, we've just always kept positive. So I get a -1 and a 4 right here. Now I need to find what my values are. To find this guy, z right here. Maybe I'll call this a, you know what, let's do ourselves a favor. X and y. We like those numbers. To find x, we lean on our friend the Pythagorean Theorem. 3 squared equals 2 squared plus x squared. 3 squared is 9. Take away 4, we'll get x squared equals 5. So x will equal plus or minus the square root of 5. In this case, we want to take minus because we're talking about an x-coordinate in quadrant 2. So x equals minus square root of 5. To find y, we do something similar. 4 squared equals -1 squared plus y squared. Well, 4 squared is 16. 1 squared is 1, so 16 take away 1 is 15. So y squared equals 15. So y equals plus or minus the square root of 15. Now, since we're in quadrant 2, a y-coordinate better be positive. So we end up with positive square root of 15. Now, go over that part of the video again because it definitely is not as straightforward as it seems to be when we just talk about it. Now, the reason we do this is so that we can get cosine of A and sine of B. I'll write that up here. Cosine of A is the adjacent side over the hypotenuse, so negative square root of 5 over 3, while sine of B is the opposite side over the hypotenuse, which will be square root of 15, all divided by 4. So you need 2 right triangles in this problem. Now, ultimately, if we come back to why we were doing this, I can now plug in for cosine of A and sine of B. Cosine of A was negative square root of 5 over 3, and sine of B was square root of 15 over 4. If I multiply these guys out, multiply the tops and the bottoms, I'll get -2 over 12. And yes, I know I could cancel some things, but I'm not gonna, just for a little bit. Minus, because the negative square root of 5, well, multiply the 5 and the 15 together. I'll end up with minus square root of 75 over 12. Which gives me, ultimately, -2 minus square root of 75, all divided by 12. And that is a perfectly fine answer. I do not require you to go further. Now, finding cosine of A minus B, which was the second part of the problem, once I have all of this worked out, so this is the bulk of the problem, we'll just come from a formula again. So, cosine of A minus B, we straight up memorize to be cosine of A times cosine of B plus sine of A, sine of B. So straight up memorization. Well, now we have all the information. Cosine of A is negative square root of 5 over 3, while cosine of B is negative 1/4. Plus sine of A, which is 2/3, times sine of B, which is square root of 15 over 4. Multiply each side of the addition side together. So we multiply these guys together on top and bottom to give me square root of 5 over 12. Multiply those guys on top and bottom together to give me 2 square root of 15 over 12. And then just combine the common denominator, but since we already have a common denominator, combine the tops to get your answer of square root of 5 plus 2 square root of 15 all over 12. And bam, you are done with this problem. But this is the key of it. Remember which direction your triangle faces. It affects what's negative. All right. In this problem now, number 9, we're after sine of 2x, cosine of 2x, and tangent of 2x if given that sine of x equals negative 12 over 13 and that x is in quadrant 3. So yet again, it's going to come down to a right triangle and some memorization. So, being in quadrant 3, yet again, I'm going to visualize where the right triangle comes from. A right triangle, if I draw an angle, will come from the side that the reference triangle is on, or the reference angle is on. So that's what my triangle will look like. So in quadrant 3, my triangle does something like this, where that's my angle x. Now, I'm given information about sine, okay? So sine is negative 12 over 13. That's the opposite side divided by the hypotenuse. The hypotenuse is always kept positive, so I end up with that right there. Now, that makes sense because the opposite side, standing for the y-coordinate in the unit circle, should be negative in quadrant 3. Now, what do I need to figure out the rest of it? I need to solve for this guy right here, which unfortunately I have to call z because I named my angle x. I'd like to call it x if I could. We do that through the Pythagorean Theorem. Z squared plus negative 12 squared equals 13 squared. Now what you ultimately get is 144 equals 169. So z squared plus 144 equals 169, which actually is very nice. You'll get z squared equals 25. Therefore, z is equal to plus or minus the square root of 25, which is 5. Now, since we're in quadrant 3, and this part, the adjacent side, stands for our x-coordinate, we're going to take it to be negative. So this side right here better be negative 5 because it stands for the x-coordinate. Now, what's this allow me to do? If you're stuck on this test, try to get sine and cosine. It usually helps. I can figure out cosine of x now. Cosine of x is the adjacent side divided by the hypotenuse. I'll get negative 5 over 13. The reason this gets us to where we want to go. In the problem, I was after sine of 2x, cosine of 2x, and tangent of 2x. By rogue memorization, sine of 2x is equal to 2 times sine of x, all times cosine of x. And now I have sine and cosine of x. Plug in appropriately, we'll get 2 times sine of x, which is negative 12 over 13, times cosine of x, which is negative 5 over 13. Well, the 13's on bottom, multiply to be 169. 2 times 5, negative 5, gives me negative 10. Negative 10 times negative 12 gives me positive 120. So bam, sine of 2x is 120 over 169. Cosine of 2x Well, by rogue memorization, that is cosine squared of x minus sine squared of x. Now that we have both sine and cosine, we can figure this out. Cosine is negative 5 over 13, so we're going to square negative 5 over 13 minus sine is negative 12 over 13, so we're going to square that. Well, when we square a fraction, we square both the top and the bottom, so we'll get 25 over 169 minus negative 12 squared is 144 over 169, which, if we plug into a calculator and we just kind of do out the math, will give me negative 119 divided by 169. I'm sorry to have to finish the problem over here, but the last thing that we would do is figure out tangent of 2x. Which we would remember to be sine of 2x over cosine of 2x. So anytime you have tangent, you can think sine over cosine, except for if you're graphing it. Well, hey, we just figured out what those were. Sine of 2x is 120 over 169. And we divide that by cosine of 2x, which is negative 119 over 169. And when we multiply by the reciprocal, so take this guy, flip it, the 169's cancel, giving me that tangent of 2x better equal negative 120 divided by 119. So the bulk of the work comes from getting your right triangle figured out, getting your hands on sine of cosine, and then just rogue memorization to get these two, and divide sine by cosine to give you tangent. So that's this problem. Gonna be one like it on the exam. All right, this is number 10. I have part A and B on the board, and now I'll get part C and D once we get these done. Part A, sine of 3x minus 1 equals 0. Do not use a trig identity unless you need to. Just gonna let that sit for a bit. In this case, I do not need to. First off, add the 1 over. Get the trig function by itself if you can. Sine of 3x equals 1. Now remember that 3x is just an angle. There's nothing special about it. So I got to figure out when sine equals 1. Well, that's at the top of the unit circle. So 3x, the entire inside, better equal pi over 2. Now on this problem, you're going to notice I said solve exactly on the interval 0 to 2 pi. And I'm going to make sure I said that, actually. Okay, I did. Whew, just making sure. So I only have to worry about one time around the unit circle, so I don't need no plus 2 pi k monkey business. All right, I just need 3x equals pi over 2. This ultimately allows me to divide by 3 to give me x equals pi over 6. So yet again, do not use a trig identity if you have to. Get the trig function by itself, and then say what angle does the inside have to be to give me a y coordinate of 1. That has to be pi over 2. Then 3x equals pi over 2, divided by 3, good to go. Moving up a notch, part B. Now I got a lot more stuff involved. But notice we can use the same algebraic tools we've been using the whole semester. In particular, I got a sine x in each term. Factor that puppy out. Sine x times what is left over? Well, that's secant x minus 2. That all equals 0. Well, now I have something times something equals 0. Set both somethings equal to 0. Sine of x equals 0, and secant of x minus 2 equals 0. Well, where is sine, the y coordinate, equal to 0? That's at both x equals 0 and pi. So bam, there's part of your answer right there. When is secant of x equal to, or secant of x minus 2 equal to 0? Well, we got some more algebra to do. Secant of x equals 2 by adding over the 2. And I'm going to highly recommend setting secant equal to 1 over cosine. 1 over cosine of x, which is the other name for secant, equals 2, allowing me to multiply up by cosine, divide over by 2, giving me cosine of x equals 1/2. Now I can do something similar to what I did here. When is the x value, cosine, equal to 1/2? Well, that's at your angles, pi over 3 and 5 pi over 3. So just some memorization of the unit circle carries you the rest of the way. Allow me to go ahead and write up the remaining portion of the review. Pause here if you need to. So number 10 still. Part C is now sine of 6x cosine of 11x. Minus cosine of 6x. I'm going to have to erase it a little bit more. And in fact, I'll only keep part C on the board for this one. Minus cosine of 6x sine of 11x equals negative 0.1. All right. So yet again, do not use a trig identity unless you have to. Turns out you got to. So this is definitely the problem where you need to use a trig identity. So whenever I'm intermingling sine and cosine, that's a calling card for a 7.2 formula. And I can write this as sine of my first angle minus my second angle. So yet again, just rogue memorization of the formula. This is sine of 6x minus, because we have a minus here, 11x equals negative 0.1. Now when I go ahead and do this out, I get sine of negative 5x equals negative 0.1. And you know what? In this case, there's no real nice angle where you get negative 0.1. So what I'm going to recommend you do here is use inverse sine, because that will at least help us get our hands on an angle where this works. So negative 5x equals inverse sine of negative 0.1. That's why we have inverse sines, for kind of crap like this, to be honest. So ultimately, x equals the inverse sine of negative 0.1 divided by negative 5. So this is kind of a goofy one because we have to invoke inverse sine, but that's what inverse sine is there for. It's when we have kind of not nice stuff. It lets you get your hands on an angle within the range of inverse sine. Let's look at the last problem on the review. I keep erasing number 10. I don't know why. Number 10, part D. Allow me to copy it down real quick. This is sine squared of x minus cosine squared of x minus sine of x equals 0. Now, if we had all of them, if we had all of them being the same, we wouldn't really have to do anything. But since there's a cosine involved and the rest are sines, we want to invoke a trig identity. The identity that we're going to invoke is the very first one that we learned. Sine squared x plus cosine squared x equals 1. Now, ultimately, I want to get this equation in terms of only one trig function. Since there are more sines, I'm going to try to replace cosine. If I solve for cosine, I'll get cosine squared x equals 1 minus sine squared x. So that's solving the Pythagorean identity to get cosine squared x by itself. Because now I can take this bit of information, cosine squared x equals 1 minus sine squared x, and plug that in where I see cosine squared x. So this is classic use of a trig identity. When we kind of have intermingled trig functions, more than one power of them, crap, we got to use it. All right, so sine squared of x minus parentheses 1 minus sine squared x minus sine of x equals 0. Distribute in the negative. Sine squared x minus 1 plus sine squared x minus sine x equals 0. And kind of combine like terms and reorder, giving us the equation 2 sine squared x minus sine of x minus 1 all equals 0. Now this lands us on something that we can factor. Remember, if you don't like seeing like sine here, you could replace this with the equation 2 times u squared minus u minus 1 equals 0. That might make it easier. However, either way, we're going to factor this. This will factor into 2 sine x, and something's going to go there, times sine of x. That will give me the 2 sine squared of x. And I need to make a minus sine of x, so I'll take a plus 1 and a minus 1. These guys will multiply to give me negative 1, and they'll kind of combine to give me sine of x minus 2 sine of x, giving me minus sine of x. Now that we've got here, the problem looks an awful lot like part B, because what I'm going to do is set each of them equal to 0. 2 sine x plus 1 equals 0. Sine x minus 1 equals 0. Getting each trig term by itself. The left-hand guy will give me sine of x equals negative 1/2, while the right-hand guy will give me sine of x equals positive 1. On the left-hand side, where does the y-coordinate equal negative 1/2? Well, that turns out to be the angles. X equals 7 pi over 6 and 11 pi over 6, just by rote memorization of the unit circle. So this gives me 7 pi over 6 and 11 pi over 6, the bottom half of the unit circle. Where is sine, the y-coordinate equal to 1? Well, that's just that. Nice pi over 2. So from that, you get your first few coordinates. From this one, you get your last coordinate, pi over 2. And ultimately, that is your answer. But it came at the cost of using a trig identity and doing some factoring. So this one's one of the more involved ones. Email me with any questions. That's it for the review. And I'll be looking at the discussion board to answer more questions come later.